Okay, so the stream should be live now if anybody wants to just try streaming it. Stream is live?
Yes. Okay, so there's a little bit of a delay because he just walked in. Yeah. So. All right.
I think we're almost ready to go. Alright, so thank you all very much for coming. I know that many of us have been at the GNU Radio conference. Can I just get a show of hands? Who's actually coming, who's not coming from the GNU Radio conference? Who's heard about things separately? And okay. That's great, thanks for coming, and also thank you everyone for coming from the GNU Radio conference. I know that we've been all, sitting all day already and enjoying some fascinating talks, but it's really wonderful of you to come out and show your support for our little meetup. It's not that little anymore, so this is really, really great to see. Thank you very much. And also thanks again to Bob. Is Bob's gone already? Pardon?
Bob's gone drinking.
Oh, okay, all right. But well,
he's gonna watch on the.
Yeah, I guess if you're watching later, then oh, Jose, is the camera rolling? Sweet, thanks. So it looks like we're all going. So thank you very much to Virginia Tech, the Hume Center, Bob McGuire, everyone that's been really helpful in organizing that. Tim O'Shea as well, and initially Tom Rondeau. I mean, Neil's going to do the full spiel, but sort of put it out there. And Jose for manning the camera at the back. Our speakers tonight for volunteering at the last minute. This all sort of came together quite unexpectedly well. So that's really great. And I also wanted to extend my special thanks to Neil as well, because he always does those amazing intros at the beginning, and he's got such a great voice for the air. So thank you for being my partner in crime in this and making it a success. And this is our 10th Cyberspectrum. We've been doing this for 10 months now, so that's been pretty good too. And Tom was remarking as well that it's amazing that so much of energy and enthusiasm has sort of happened over time with STI. Anyway, I'll stop my rambling. Thank you all again, and I'll hand it over to Neil, and then we'll kick off. Take it away, Neil.
Good evening, everybody. My name is Neil Pandya. I work for Edis Research in Santa Clara, California. I'd like to welcome you all to the 10th monthly Cyberspectrum Meetup. This event series serves as a forum for the exchange and knowledge of ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event tonight is a special edition of the Cyberspectrum series on the East Coast here at the Virginia Tech Research Center in Arlington, Virginia. This occurs as the GNU Radio Conference is being held in Washington, D.C. this week. Free pizza and soda is provided in the lobby, courtesy of Bastille Networks. Our first speaker tonight will be Richard Prestige from the National Radio Astronomy Observatory, who will talk about using SDR and GNU Radio in astronomy applications. Our second speaker will be Tim O'Shea, who will talk about some more of his cool GNU Radio hackery. GNU Radio lambda blocks are simplification of pure Python blocks for GNU Radio, which allow for writing a new block from within GRC with a simple Python lambda expression. He'll demonstrate the great signal processing hackery that can be achieved with the stream and message versions of this block. Our third speaker will be Kiran Kara, who will talk about PSK modems in GNU Radio. PSK modems in GNU Radio have typically used tracking loops which take time to converge and do not leverage reference signals. Through rethinking the approach to PSK demodulation in a message and burst-based context, a robust new way to build modems is demonstrated. Our fourth speaker will be Tim Keister, who will give a presentation titled Hacking an RF Shock Collar. GNU Radio is an awesome tool for reverse engineering, but people seem to get stuck somewhere between complex to MAG, Audacity, and MS Paint. It's not as hard to get packets out in real time as you might think. He'll build a transceiver from the ground up for a shock collar from the Wireless Village at DEF CON 23. All Meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The previous 9 events have already been posted in full HD video. We have set up a channel in IRC called #Cyberspectrum on Freenode as a way for people remotely watching the live stream to contact the group here in Arlington with comments or questions and alert us to any audio-visual problems. Future meetups will return to California and will continue to alternate every month between Noisebridge in San Francisco and the Edis Research Office in Santa Clara. The next meetup will tentatively be held on Wednesday, September 30 at Noisebridge in San Francisco. Further details will be posted on the meetup webpage shortly, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. As always, if you'd like to present something or you have ideas about future topics, please let us know. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Virginia Tech and the Hume Center for providing the space and hosting the meetup, as well as Bastille Networks for providing complimentary pizza and soda. We would also like to personally thank Dr. Tom Rondeau, Tim O'Shea, Professor Robert McGuire, Dr. Charles Clancy, Seth Heightfield, Christine Carlson, and Anna Guest. Their help was instrumental in organizing and promoting tonight's event. At this point, we can get started, and I'll invite our first speaker to come forward.
Thank you, Neil.
Yeah.
Oh, you want to?
I can just put my own laptop over if that's easier.
I'll let you drive. Should be on the flash drive. Stuck in. Should be able to open it directly.
You need a hand or
Slow too.
sure you want to use that my laptop?
Maybe not. I can just pop my.
Okay, yeah, let's do that.
Wait. Oh, yeah. I hope there wasn't an O-Day on that USB stick.
NRAO USB sticks.
Neil, somebody named Ion Berkeley on the channel just said Neil needs to spice it up some.
Okay, so thanks everyone, and I'd like to also thank Tom Rondo and Balint for inviting us here and allowing us to talk. fraud because we're actually not really using SDR in astronomy at the moment. We plan to. So I'm representing a loose collaboration of about 8 of us. A couple of astronomers, a couple of hardware engineers, a couple of software engineers, and a couple of university professors. So we, for a whole variety of reasons, have realized that the time is right for us to start looking at SDR generally and GNU Radio in particular. So 4 of us are here in the room, 6 of us came to GRCon, and we're basically learning, but we thought it would be useful if we could tell you a bit about what we're up to and hopefully make some more contacts and collaborations. So 2 of us work for the National Radio Astronomy Observatory, which is the US organization set up to operate radio telescopes that are too large for any individual university to operate. So we've been in existence since 1956. We have 4 main telescopes. Do you guys have a pointer or I just use it? Let's use it. So the Green Bank Observatory in West Virginia, the ALMA Atacama Large Millimeter Array in Chile, the DLA in Socorro, and the Very Long Baseline Array, which is 10 25-meter antennas spread across the continental US and the Virgin Islands and Hawaii. So it forms a virtual telescope, pretty much the diameter of the Earth. And we also do VLBI with a Russian satellite, so we have an extremely long baseline that goes a long way out. And then we have a development lab in Charlottesville where we do basic engineering research. So this is our mission statement, which you can read for yourselves, but basically the reason that we are interested in GNU Radio now is that we need the next generation of engineers. We're finding it difficult to find graduate students who really have a deep understanding of DSP and who can get hands-on and build instrumentation for us. So also the NSF these days is extremely keen that every research proposal has a strong broader impact aspect to it. So we have been doing outreach to middle schools and high schools for years, but we're looking to do that more with some DSP techniques. And then the third one is to promote astronomy to foster a more scientifically literate society, and GNU Radio can help us in all of those. So this is our old telescope in Green Bank. It was built in the early 60s. The National Radio Quiet Zone, if you have heard of that, was set up in the late 50s to protect the telescopes, so no cell phone coverage in Green Bank. And then one night in 1988, the telescope unexpectedly collapsed, and the press claimed it was because we were trying to find them. But fortunately for us, as a result of that telescope collapsing, we got money to build the new Green Bank telescope, which is a 100-meter diameter, fully steerable telescope. It can cover 85% of the whole sky from Green Bank. It's the largest fully steerable telescope in the world. 2.3 collecting area, 2.3 acres collecting area, so you get 2 football fields in the dish. It's really quite unusual telescopes for a large radio telescope. It's the only offset aperture telescope. So in this picture, or maybe in this picture, the telescope is not pointing in this direction, it's actually pointing more in this direction. So the radiation comes in, hits the subreflector, goes to the receiver cabin, and all of this feed arm is outside of the aperture. So it has extremely clean optics, very high dynamic range, much more resistant to RFI in the radio quiet zone, etc., etc. So we do a whole range of science, from solar system stuff to history and evolution of the universe. So this is a map of the local supercluster of galaxies And by looking at neutral hydrogen line emission, you can get redshifts and three-dimensional positions. And so there was a group in Hawaii, so it's called the Laniakea supercluster, basically mapped out where every galaxy is and could work out the potential wells of this supercluster and which galaxies were associated with which. We do bistatic radar imaging of the moon. I'll tell you a bit more about that. When the Phoenix lander landed on Mars, NASA transmitted to an orbiter, which then transmitted back to Deep Space Network, and we could track it directly for them. So we were actually the first telescope. We knew it had landed successfully before NASA did. This is a time frequency plot. This is a streak of RFI, but this is the lander coming down here. You can see it starts slowing down. So guess actually starts here. It's going this way. Starts slowing down across here due to atmospheric friction, and then the parachute deploys, and then it lands. So just very quickly, 2 research highlights. This is bistatic radar imaging of the moon. Arecibo, the 300-meter diameter telescope in Puerto Rico, transmits, we receive. So you can make 2D plots that have frequency on this axis and delay on this axis. And so this is the footprint of the beam on the moon. But because you can measure frequency and time delay incredibly accurately, much more accurately than you can make equivalent observations, just 2D positions. We have a model for the moon, and so if you have a Doppler shift, you must be somewhere on this circle because the moon is rotating, and you have a delay, you must be somewhere on this circle because the further away you hit the moon, the longer the delay you have. So knowing the geometry of the moon, you can convert that into an actual image of the moon, and then you can just zoom in on the South Pole, and we can make images that are about 150 meters resolution on the surface of the moon. So it's a significantly higher resolution than the HST can get, the Hubble Space Telescope. So the only thing that makes higher resolution images is orbiters actually going around the moon. And radio waves actually go through the regolith, so optical images, the sunlight bounces off the very surface of the moon, so off the dusty layer. And this is 70 centimeter wavelength. Radio waves, they go a few meters into the regolith before they get reflected. And so by looking at the circular polarization ratio of your return signal, you can detect signatures of ground ice in the regolith. And our conclusion, looking at one equator that is at the North Pole, so it's continuously shadowed, it never sees the sun, and then another one that does see the sun, their CPRs look basically the same, so we concluded there is no ice at the South Pole. The other one is pulsar timing. The GBT in particular spends a huge amount of time doing pulsar timing. We can measure, so pulsars are rotating neutron stars, strong magnetic field, and as the neutron star rotates, we get a beam of radiation sweeps around over us. This MJD is days, so these days along this axis, and residuals on this plot in milliseconds. So if you time the pulses, you can measure them so accurately that you can predict when every single pulse should arrive on the Earth, and then you can start fitting for different effects. So this is what a fit would look like if you had the wrong position on the sky for the pulsar, so the pulses wouldn't be arriving when you thought they should. This is if you've got the rate of slowdown of the pulsar incorrect, and this is if the pulsar has got a sideways velocity across the sky. So as time goes by, its position gets worse and worse. So if you fit for every parameter for the pulsar, so its position on the sky, the pulse period derivative, you can get very accurate predictions, and so you can do things like test theories of general relativity. So if you have a pulsar in a binary system, so this is the pulsar, this is another star. As the pulses go past the other star, they fall into the potential well and come out the other side. And this is the prediction of general relativity as to what the residuals should look like as a function of position around the orbit of the pulsar. So far, general relativity still holds, and these are the most extreme gravitational conditions that we have been able to test GR in. So the next thing we're doing is looking for gravitational waves. So if you have two supermassive black holes at the center of a galaxy, so two galaxies collide with each other, they merge together. Every galaxy pretty much has a supermassive black hole, like a 10 million solar mass black hole. They start spiraling around each other. They give off gravitational waves, and these waves travel through space, and they perturb the position of this pulsar, and they perturb the position of this pulsar. And looking at the timing residuals of when pulses hit the Earth, you can detect these gravitational waves. And it is just like the LIGO project. So LIGO, they have I can't remember how long these are, sort of kilometers. They have mirrors at the end of these tunnels, and they have test masses, and they have to detect the test masses being shaken around by gravity. They haven't done that yet. So LIGO is sensitive to gravitational waves with frequencies of about 100 Hertz. We are sensitive to gravitational waves with frequencies of nanohertz. So this observatory is called the Nanograv Observatory. And there's really a very well-defined prediction for, so this is timing residuals you would expect in milliseconds. This is time in years that you have been timing a set of pulsars, and you get these predictions for where the gravitational wave background should be. So currently we haven't put any interesting limit on it. So this slide is a bit out of date, because in fact in 1915 we still haven't put a really interesting limit on it, but better than it was back in, I think this is a slide I got in 1913 actually. I have to update that. And then a very exciting new thing, which will segue into Dave McMahon, who's going to give the second half of the talk. Back in July, a Russian billionaire, Yuri Milner, who I understand sort of started the Russian equivalents of Facebook and everything else, has donated $100 million over 10 years to search for extraterrestrial intelligence, SETI. And in particular, the GBT is getting $2 million a year for the next 10 years to fund this search. And that is being executed by guys at UC Berkeley who are responsible for the SETI at Home project. So I'll just say a couple of things that I'm going to hand over to Dave. So we have been doing digital signal processing for the last 50 years. We build our own receivers. We have HEMT amplifiers cooled to 15 Kelvin, so very low noise amplifiers. Typically amplifiers maybe 6-8 Kelvin. We're looking out into space, not at the ground, so our total system temperature can be as low as 20 Kelvin. We have our own DSP framework project called Casper, and for a variety of reasons we are interested in maybe aligning that with GNU Radio in some way. So Dave, if you're over there, Dave's going to spend 10 minutes talking about the Casper project and how it might overlap with GNU Radio. And so you've changed your presentation, so you want to use
slides, right?
Yep, I have slides. Yeah, they're all in here. Yep, there you go.
Just got some backup material.
Okay.
Yeah. Hi, thanks, Richard. I roped Richard into giving this talk today, and so he paid me back with the same favor of giving us half of the talk. goes around comes around. So I'm going to talk mostly about Casper today. This is sort of why I'm here, is because Casper is this collaboration that we started back in about 2005 for astronomical signal processing and electronics research, as it says. The PI is Dan Wertheimer, who started the whole thing back then. He's also the chief scientist for SETI at home. It really started with a synergy between this group within the EE department at Berkeley. They were building these ASICs, and they wanted to have some way to emulate them, so they started building these boards that had FPGAs on them. And so they built this board called the B board, BEE, which was the Berkeley emulation engine. And then they built another one called the B2. And that was sort of where we got involved with them. We went down to one of their lunch talks. They had free lunch for people who went to their talks. So we'd go down there and check them out. And they had this FPGA with tons of processing. I thought it was really great. So we started to use their board, and they had this sort of tool flow, Xilinx FPGAs, with Xilinx tools, and they had this whole wraparound with MATLAB and Simulink and System Generator, which is another Xilinx product to do FPGA design. And so it's all a way to build the gateway for the FPGAs and kind of hide the details of HDL. It was kind of very similar, in fact, to, well, not very similar, but kind of like what GRC does. And so it's a block diagram thing. And so that's kind of why we're here. We want to use GRC, see if we can use GRC to be a design entry for us instead of using the Simulink stuff, because it's kind of our tool flow that we've sort of wrapped around it all is getting a little old and creaky, and we want to kind of update things a little bit. And it's closed source. We kind of prefer open source, being in the academic community. So anyways, this map shows Casper collaborators that we have around the world. All these are basically radio astronomy observatories or people who use Casper hardware. Kind of cuts off a little bit on the sides, but gives you a sense of it. It's really, if you go to any radio astronomy observatory in the world, the chances are they have some piece of Casper hardware somewhere there. So this slide talks about some of our goals and things that we have. We want to use standard hardware components, reuse things. We want to not have to reinvent the wheel every single time. We all kind of do the same things, but only different, so we kind of try to share as much as possible. And it's been very successful, but it's getting a little bit, like I said, old and creaky, so we're trying to find some new ways to update things. This is a picture of Roach board. This is Vertex 5 FPGA here. There's some ADCs that we have. We have some ADC boards that we have, and this is an older board that had these 10 gigabit connectors here called CX4 connectors. They're kind of like InfiniBand, 4 copper pairs come out each direction. It's kind of this big fat cable. It's kind of clunky to work with. These yellow blocks kind of show some of the block diagram things we have. This is a 10 gigabit Ethernet core. So your data goes in here, you tell it when it's valid, and you say where you want to send it, and every end of every packet you say end of frame, boom, there goes your packet. And you can receive data as well. That comes up the other side, and data that comes to you from the network. This is the Roach 2 board. This one is sort of the successor to that. This is Vertex 6 FPGA. This particular one is one that's in use at Green Bank. They've kind of mounted it on this plate so that you can install it as a blade in the rack. Most other places have them installed in little 1U chassis. These are the ADCs. These sample about 5 gigasamples a second maximum, but I think you guys are doing like what, 3 gigasamples a second? And a bunch of ribbon cables for, I guess, calibration signals and control signals and such. And this is a synthesizer to generate the sample clock ball. And this is a picture with LEDs, I guess. This is kind of a block diagram, schematic. I won't go over all this detail now. Just a lot of stuff. Basically, we have Vertex 6, and then we have a little power PC that sits off the side. That's kind of a carryover. The old days, we had Vertex 2 Pro FPGAs, and they had the power PC core right on the same die as FPGA. And that was really kind of neat, except you look at the die and you see, why do they have this huge space in the middle? It's like, oh yeah, that's where the PowerPC is. It's like, well, that's a $20 chip. I'd rather have more gates there from the FPGA. So eventually they pulled it out. Now they're going back, I guess they're putting the ARM cores back in the chip, but I think they're a separate layer that kind of stack them on top or something. This is another slide that shows our yellow blocks and the system generator block. So these blue ones are Xilinx blocks that come with system generator. They have things like adding and comparing and multiplying and such. And these yellow blocks are more of the blocks we've wrapped up. They kind of interface with the PowerPC behind the scenes as well. So some of these are like shared VRAMs, so you can put in test data vectors and things like that, and you can drive test patterns through your system for testing. Here's a picture of the GBT spectrometer. These are the blades that we saw earlier, all flat. It's all mounted in a rack. Green Bank. Lots of stats about that stuff. And here's our wish list. This is what we kind of want to have in the future. It's kind of just a dream wish list, but hopefully we'll realize it. We have a lot of I/O needs, and we have a lot of ways to boards. We need to interconnect them, and so it's just a lot of data that we have. We sample very fast. Green Bank, they only have one antenna, but it's a big one, but it's only one. Other places, they have arrays of antennas, and so there's this project we have in South Africa. They have 128 antennas, dual pole antennas, and so we can bring all those signals in. And it's all the electronics have to live in this little shipping container that's out in the middle of the desert. So it gets a little bit crowded. And then software firmware wish list. This is maybe more where the GNU Radio side can kind of offer us some ideas. Open source design tools is way preferable for us. I'm sorry, what? Louder?
Sorry, a request. The audio levels are a little bit lower in the mic, so you speak a little bit louder than the network.
Okay, sure. Yeah. So open source design tools, get rid of MATLAB, simplify the design tools, but every instrument is a little bit different. Every observatory has their own way of doing things, and so you have to have some level of customization. It's hard to make a one-size-fits-all spectrometer for observatories. And astronomers really like to get performance out of their FPGAs. It's kind of, they want to do as much as they can for whatever their budget is. And so if you give them an FPGA, they want to kind of do as much as they can with it, so they don't buy 2 FPGAs. So they really want to be able to optimize the performance of their hardware, software, and get as much as they can out of it. So we'd like to use industry standard libraries. We don't want to use custom MATLAB draw scripts. That's what we kind of currently do. There's a whole thing. You can make a block diagram, you can parameterize it, but it ends up that people over the years have gotten frustrated with some of the limitations of that, so they write scripts that actually draw the block diagram from a script, and it's kind of like a strange, topsy-turvy, convoluted world where you have a program that generates a block diagram because you want a block diagram because you don't have to write a program, but anyways. And we want to get maybe away from being so tied to Xilinx. They've been very, very good to us with the Xilinx University program, and so they've been very generous to us. But we have a lot of other hardware that other people have or they have provided to us, and it'd be nice to be able to target maybe Altera platforms or other kinds of FPGAs. So that's why RFNOC is kind of interesting to us. We want to check that out, see if that maybe has some ways we can incorporate that with our stuff. And then this is getting back more to what Richard's working at NRAO with the SDR, GNU Radio stuff. Do you want to talk about that?
Yes, I come back.
Yeah.
So thanks, Dave. So we have
Sorry, just before you go, I didn't get a good shot of you with some of the cool hardware. If you go back a couple of slides, so we can get some really cool stuff
so.
That's good.
Yeah.
Do the head, yes.
All
right.
Ta-da.
So, right now we've just finished this spectrometer. That's just final stages of commissioning. We are working pretty closely with a bunch of universities. UC Berkeley, Brigham Young University, they do a lot of beamformer development. And we currently have a $4.5 million proposal into the NSF, which hasn't been rejected, although other people's have. We haven't heard that we've been accepted yet. But a big chunk of that is to try and get a richer range of undergraduate teaching materials. And what we're particularly interested in is teaching basic DSP concepts, not like how to build new radio applications. But we're really keen to have sort of lab work that will go along with the classwork. And at the same time, we're interested in using GNU Radio, as Dave said, potentially as a front end for Casper. We've learned a huge amount in the last few days, certainly learning about a lot of the GNU Radio display tools. I did not know many of those existed, so like Phosphor looks absolutely fantastic. This is what we could bring to a collaboration. Radio astronomy is a really great way to grab like kids' interest in the science. Astronomy covers, you can look out there and see stuff. It covers physics, it covers computer science. It's just really engaging. We do have professional EPO staff at our site, so they know how to create good curricula and material for middle school kids, high school kids. We do have really very experienced electronics and software engineering staff, although they don't have a lot of spare time. And one thing we could bring is that we have a lot of expertise in the analog and sort of antenna regimes as well as the DSP stuff, so we could design interface boards or starter kits or whatever. And we would be really interested in showcasing GNU Radio in some real state-of-the-art astronomy research. So we typically have sustained data rates out of our backends, can be as high as hundreds of megabytes a second until we fill up a petabyte of disk space. Then we have to stop because we can't afford any more disk space. But we are putting massive amounts of data through a quite impressive DSP tool chain. So that's the last one. These are us. Thanks for listening. We'll be around for the rest of the, tomorrow anyway, so we'd love it if anyone wants to come up and talk to any of us. Thank you.
Thank you very much, Richard and Dave. Radio astronomy and space in general is always such a cool topic, so that was really nice to hear about how SDR is being used there. So, any questions?
I assume you're measuring millihertz over years. What kind of clocks are you building? What do you use to do that?
Yeah, so we have hydrogen maser on site. So we have we use GPS to get the UTC time, but we have a hydrogen maser that's stable to picoseconds over timescales of hours. And I don't know what's the sort of long-term stability of our timing. We get something like 10 significant figures on the pulsar period. They're typically, millisecond periods, hundreds of milliseconds, accurate to 1 times 10 to the 10.
All right, any other questions? Another one back there.
Yeah, I just want to make sure I got the Casper website. Is it casperberkeley.edu?
Yep.
Information on Casper.
All right, thanks. Let's thank both our speakers one more time. And we'll head on directly to our next speaker, Tim O'Shea, who's going to talk about some crazy GNU Radio lambda hackery. all the connections you need?
I think so. Find out shortly. All right, so this is a
No, it's not. Success.
where's that tab? That is Mount Pilatus. And
Did you take that photo?
I did. I've messed up all the settings.
Yep, there you come.
Let's run away.
Slide it over.
There's like a 2,000 pixel gap between the screens right now.
Should have control panels. sticking
Not sure
together.
I ever knew that was possible. There are displays 2 and 3. Alright, so we'll move this over.
Probably do the other one plugged in.
Let me redo this. Sorry.
Wouldn't have anything to do with the dongle that's like on the other side.
That's a good question.
Do you want a mouse, by the way, since it's the...
No, I'm fine. Thanks.
It's easy for the radio to track that.
Do this all at once.
There we go.
Alright. Linux makes everything fun. Alright. So I'm going to talk a little bit about a thing I introduced to GNU Radio out of tree right now called the GNU Radio lambda block. And this is really just taking the Python like lambda expression and wedging it into GNU Radio has these pure Python blocks, right? So traditionally in GNU Radio, your blocks are all written in C++, wrapped in Swig, and then instantiated in Python. So you can use Python to kind of tie them together, but actually the work functions are in C++. Now the pure Python block is not that. So in the pure Python block, you can actually write a work function in Python, and then it basically passes the raw buffer back down to C to hand your data off to another block through a stream port or a message port. So there's this thing called a pure Python block in GNU Radio where you can just implement blocks, whether they're stream or message, in Python. So that's not too bad. It's a nice way to like prototype because these things are very quick to write and they're a lot less error prone than dealing with C++. And so it's a great way to prototype your application and then benchmark and then port the hotspots into C. Is kind of a way we operate a lot. So I'll show you, this is an example. This is actually the PDU block, or the PDU lambda block, but this is a pure Python block, right? So you simply inherit from this gr.syncBlock class in Python. You implement a constructor, and you implement a handler. So it's very simple, but you still have to create this Python file. You have to create an XML definition, and then you install them into your prefix somewhere. And so that's a great way to do blocks. But the whole idea of these lambda blocks is just to have something even quicker. So like, if I'm sitting here in GRC and I would just want something that gives me like an envelope of a signal, or I want to just take signal squared. And there's a lot of those operations are already created in GNU Radio, but sometimes you just want to throw something in there and you don't really care how fast it is. You're just running it on a file, you're testing, you're prototyping, you're not going for speed yet. So you want just a really quick way to throw something in there. And so that's the whole idea of the lambda block. It's pretty simple overall. So I was going to show you two versions. So first is the message version, and these are really the same. They're just, one of them implements a message handler, and the other one implements the GNU Radio work function in a stream. And so
in the message version, so there's this tool called Such Samples, which I showed off the other day at GRCon, and I'll pull this up and just show you briefly what's going on here. What happens is this is entirely message-based file plotting tool in GNU Radio, and so every time we move this slider, it sends a message with an offset and a length, reads that offset out of the file, and then sends it to these plotting tools, which just plot that chunk of data. So if we go to an offset like the one we just saw, here we have some FSK signal. I'm again using Phil's wonderful data set. He hates when I mention that. All right. So these are two default plotters. We're not doing any operation on the data, right? This is just the raw file from disk, right? And so this is the time, right? This is just the I and Q raw time values. So if we want to do something like compute a power envelope over time, we can drop a PDU message lambda block in. We'll copy this time plot, and we'll just call this power. We'll connect it to this lambda block. We'll take the same PDUs here from the message source. And here we just define whatever expression we want to map through this block. So let's just say x times x, we'll take x squared. Well, all right, we might want to multiply it by the conjugate to really get the, yeah. We'll do times 2. It might work on a vector, we'll see. Well, that's the same thing. All right, so. All right, so there we go. It's like the fastest block ever inserted into GNU Radio, right? And so if you're doing some hackery, it's just really a fast way to throw something in there that you want. So now maybe we just want like, some weird x to the third with a conjugate in there, right? So there, you could be doing something weird where you just want to try out new metrics, try them on your test data, and it's just a simple way to do it. And we can still just kind of scroll around in the file and like look at the behavior of this guy. At interesting parts in the file if we want. All right, so this isn't a particularly useful metric, but this is an exercise left to the user. All right, so you can do the same thing in a stream. This is that same file. This time we're streaming it from a file instead of pulling messages out of it. So let's go ahead and just disable this stuff. Ignore all those blocks. So here we'll put a stream lambda block down. And what's cool is you can change the input and output types to whatever you want. And it's just going to use NumPy types in the lambda expression. So you're really just dropping a NumPy mapping in here. It's pretty simple. And it's actually, so looking at the performance, NumPy is pretty efficient. Your only penalty is the function call overhead to Python and back. So as long as you operate on big chunks of data, it's actually not terribly slow for some of these things. So if we look at the expression here, we're mapping input items, which is a vector of the input vectors, same way you'd get in a work function, to basically a vector of output vectors. So you can do end-to-end streams in these things like you could in a normal stream block, and you're just dropping in here. So all I'm doing here is striding by 2 in the input vector, squaring it, and then multiplying by some scalar. So again, this is some useless arbitrary operation, but you could put something useful in here if you were inclined. And if we auto scale, we're streaming through just fine. So,
Question?
yep. So the question was whether the vectors are converted into like a Python list or some type on the way in and out, and they're not. So the GNU Radio pure Python block actually does a little trick, I think, mostly sure of this, to like raw copy the vector contents to the right NumPy vector type without a memcopy or some sort of a list representation. So the actually in and out of NumPy vectors is pretty efficient. So really your only overhead is like calling the pipeline interpreter, calling the NumPy function. And then everything else is pretty optimized. It's not a custom volt block, but you can do that for some extra time. Yeah.
Does the lambda function receive the same parameters as the work function? The vector of sampling? They receive one.
Can you repeat the question?
Yeah. So the question was whether the Python or whether the lambda expression gets the same like call arguments as the work function. So it's slightly simplified. So these are like a subset of what you can do with a work function. They're not as expressive because we boiled it down to a single function call, right? And you're in a work function you can set outputs iteratively. You can return different amounts on each stream. Here you have to write a single expression that returns your output vectors. It's kind of like a functional style of doing it, right? And
those two arguments, input items and out items,
right.
are the same as the work function.
They are, but for instance, general work is more expressive than the sync work function. So you can't do everything you can do in a block with one of these, but you can do a lot of operations. So like for instance here I am striding by 2, so this is a decimating by 2 block. So you can do like basic rate changes and things with this if you want to. And the way we're outputting a tuple here, or like this is like in the parens is a list of one item. That's like the first output port. Right? So you can return basically n expressions where each one is a different output port. So, yeah.
Do you have history available in L?
So right now there is no history. I think you could start adding all of the features from a normal block into this, and I don't know to what extent to go with that. So I guess, so a lot of my motivation for this right now is in GNU Radio we have message blocks and we have work like stream blocks, right? And they each have a totally different kind of way in and out and API for how you write a handler with PMTs and how you write a stream function with these input and output pointers. And so this is kind of starting to try to unify them to like a common expression so that we can easily move functions between stream and message blocks without having to write a specific one for each. So what I'd like to do is keep a kind of a simplified subset which doesn't have things like history to worry about, and have kind of this unified lambda block where you can write some lambda expression, instantiate it as either a stream block or a message block, and use it kind of wherever in your application that you want, wherever it makes sense. And certainly like there's a lot more thought to be put into how things like history or zero padding or things like that fit into this model. And I don't have a really clear picture of that, but this is kind of one of the things that I'd like to tackle with this functional architecture for signal processing working group, or FOSS working group that I've been kind of trying to lead up. And so we're meeting Thursday, tomorrow, I think, to discuss some of this. And I'm really interested in just kind of how people will use this and like what the shortcomings are and how we can encompass all blocks into this kind of a simple model at some point, maybe. Or like doing C code generation from the NumPy expression. There's a lot of cool things like Theano is a really cool library that takes these NumPy expressions and compiles them down into CUDA. And so could you do something like this where you just map a bunch of these lambda blocks down into CUDA? So yeah, that's pretty much what I have. Any other comments, questions?
Yeah. The work function looks like it's got a for loop
question was, it looks like there's a for loop in the work function, and for loops are scary, so we might want to remove it. So this for loop is looping over the number of output ports. So yeah, you could probably turn this whole thing into another like map lambda.
Okay,
thing.
That's number of ports. That's
Yeah, it's not looping over items.
Thanks.
Yeah. Yep. Very functional. All right. Thanks.
Okay. Any other questions for Tim?
Oh yeah. So lastly, this is in my grpyqt out of tree repo. So if you want to play with these, install grpyqt. And there's some write-up on my blog at o'shearesearch.com. So go read those if you want more depth, or come talk to me.
Thank you very much, Tim. Many of you probably already know Tim is one of the GNU Radio core contributors and has written some really cool stuff. So if there's some sort of nitty-gritty about GNU Radio you're interested in, he's certainly one of the guys to talk to. So I thought maybe we could take a couple-minute break. I think there might still be some soda outside if you want to hydrate a little bit, or just stretch out. And we will resume with our next speaker in 5 minutes. That's even better.
No, they don't. They anchor themselves down to the ground. Stick like
name is Kieran. I work here at the Hume Center with Tim, actually, closely on a lot of projects. And the past year and a half, I've learned a lot about GNU Radio. As part of this, I'm kind of new to this.
Louder, please.
All right. And so what I'm going to talk about today is receiver synchronization, and specifically a receiver synchronization algorithm that we use for a burst modem. And I do apologize, I didn't have time to put slides together, so we're just going to use some pictures off the internet. But this is part of what I wrote up for this project, so it's not complete plagiarism. So kind of the background and the problem that we're trying to solve is that, there's a lot of GNU Radio blocks in order to do synchronization, and a lot of them use phase lock loops and frequency lock loops, and these work really well for continuous time signals, where you have the signaling never goes on and off. So the phase lock loop and any of the other loops that you have, they can maintain tracking. But when you have a bursty signal, you can still use phase lock loops in order to do synchronization of the signal, but we decided to go a different approach. And part of the reason for that is we just wanted to kind of try and see how this performed versus the original design, and just gave us another opportunity to write a new block. So that's what we did, and that's what I'll talk about today. So by bursty signal, what I mean is, and I kind of already went over this, but you have your transmitter and it's signaling on and off. So it doesn't continually transmit a signal. I think TV signals are continually transmitted. They're always on, whether there's anything to broadcast or not. But modern communication systems are going more and more bursty. They're not always on. And so how do you synchronize a signal? So you guys probably all know this, and I'll just quickly go through the background of why you need to do synchronization. So by synchronization, I mean you have to do three things. You have to do time synchronization, frequency synchronization, and then really you also have to account for the wireless channels, whatever impediments the wireless channel imposes onto your signal. By time synchronization, I have a simple graph here, which shows what really I mean by synchronization. Suppose that I have this sinusoid and I'm sampling the signal, and I'd like to know the peak-to-peak voltage of the sinusoid. Well, and I'm going to get digital samples of the signal. Well, I need to sample this signal at the peak moment, right? And that's what the blue arrow represents. Is it's sampling. You've got your clock, and suppose that you take samples on the rising edge of your clock. The bottom clock is a properly aligned clock. So it's proper because this is what we want it to do. We want it to sample the sinusoid at its peak voltage, and it's basically its maximal value and minimum value. If you don't have a properly aligned clock, such as the one that's shown on the top, and you sample on the rising edge, you'll see that you won't. The previous rising edge, if you can see my mouse, is right here, and the next one's right here. So you actually miss the peak. So this is, in essence, what time synchronization is. This is a very simple example. You're not sampling sinusoids usually. You're sampling a digital communication signal. But you need to have your receiver clock assigned or aligned to your transmitter clock so that you can sample at the optimal point. So that's one of the things that we need to accomplish. So this block that we built does this, and it does other things too, but I'm talking about what are the impediments. So that's at a high level what time synchronization would do. So let's talk about frequency synchronization, and these concepts are related, but suppose I have a QPSK signal, and the constellation of a QPSK signal, suppose that my symbols are mapped on the IQ plane as follows, shown by the blue dots. If I have perfect synchronization in frequency, then when I've received and demodulated, when I receive my constellation and done all the acquisition algorithms, I should have my received constellation show up on points that are shown by the blue dots. If you have a frequency offset, what you'll actually see is a rotating constellation. And it rotates at a rate that is proportional to your offset from the center frequency that's being transmitted. obviously don't want that either, because if you have a rotating constellation, well, you're not gonna properly map your received symbols to the bits, because each one of these symbols represents 2 bits in this case. So you want to be properly frequency aligned as well. You can also actually have a constant phase shift, and what that will do is all your constellation symbols won't rotate, but they will show up. They will be rotated, but they will be static. As shown kind of by the X here. So if you imagine just the X's without arrows, that is you receiving the signal. You have correct frequency synchronization, but you don't have correct phase synchronization. So these are kind of the effects that we need to account for in any receiver before you can actually demodulate a signal. Finally, we all know that multipath is a big impediment to wireless communications. Well, impediment's the wrong word, because some communications protocols actually use multipath to their advantage. But in this case, we were developing a burst QPSK modem, and it wasn't anything fancy, so we had to account for multipath. Multipath didn't help us in this case. So what this diagram shows is it is the impulse response of a channel that has multipath. So we can kind of break this down a little bit more. If I transmit a signal, from linear systems theory, we know that the signal that I receive is the convolution of the transmitted signal and the channel. If the channel only has one component, like this, then I will receive the signal that was exactly transmitted with some gain. Really, it's some loss, because, well, you're losing power as the RF signal travels. But that's what the arrow here represents. But if I have more arrows, that means that I'm receiving multiple copies of this signal. And Balint talked about visualizing multipath. This is the mathematical way to represent a channel that has multipath components. So this is just an example that shows 3 multipath components. And you can kind of think of this as the weight at which each of the components is received. And so the first component that I receive is the strongest, the second one is the weakest, and the third one is actually a little bit stronger. And this is not an unrealistic scenario. This is probably simplified in the sense that you may have more than 3 components in a scenario. It really depends on your environment. So these are the 3 things that this block that we built attempts to correct for. So how do we do this? Well, one of the things that we have to realize is that this is the impulse response of this channel. But the impulse response of a channel is actually in real life time varying. So this is the impulse response of the channel at some time instant t. But at some time instant t plus 1, it could be completely different. The first component could disappear, the second component could be strong, and the third component could be weak. So the point of recognizing that in light of a burst modem is that you need to model the impulse response of each burst independently in order to properly demodulate each burst. You can't say, well, my channel was X at time t, so at time t plus 20, the channel will still be X. You can't make that assumption. Okay, so how did we attempt to solve this problem? We took an adaptive filtering approach to solving this problem. And an adaptive filter is the general block diagram of an adaptive filter. And the input to the adaptive filter here is x of k, and the output is y of k. So I guess I should back up just a little bit. We view the synchronization problem here as just a filtering problem. And what we want to do is find the optimal filter which will correct for all 3 of the effects that I mentioned above: time errors, frequency errors, and channel effects. So what we want to do is, at a high level, we want to say, I have this input signal. I would like to find the optimal filter weights such that my output signal looks like some desired signal, D of k. And that's what this block diagram shows here. Well, the whole point of communications is, if you knew what you were communicating, if you already knew D of k, then there would really be no point in communicating it. So how does this fit into the context here? Well, typically for burst signaling mechanisms, they'll have a preamble attached to the front of the signal. And you know exactly what that preamble is before you start communicating with each other, at least at a simple level. And if you know what that is, and you know what you've received, then you can essentially use this filter structure in order to determine the optimal weights, such that the received preamble sequence is going to be as close as possible to the reference preamble sequence. And that's, at a high level, what the adaptive filter is doing. It's comparing the received preamble sequence to the known preamble sequence, and then in the MMSE sense, it's going to compute the optimal filter weights. Once it computes the filter weights for the preamble, it's going to then apply that filter to the rest of the payload, which is unknown. And so one of the fundamental assumptions here, remember we were talking about how the channel may be varying with time. You assume that the channel is constant over the length of your burst, because we're not doing any adaptation or changing of the filter weights while correcting a burst. So at a high level, we want to use an adaptive filter to solve this problem. And an adaptive filter, all it's doing is it's finding the optimal filter weights. Sorry, go ahead.
So does that sort of determine the size of the burst? Does that limit the size of the burst?
It does. So if you're going to design a comm system such that, suppose you were designing a comm system and it's going to use a burst signaling, and you know the environment that it's going to stay in, you ideally want to have some measurements of what the coherence time of the channel is. And that will determine your maximum burst level, if you don't want to do adaptation in between the burst. Now, there are signaling mechanisms where they have preambles interlaced throughout the burst. And so you can say, well, I'm going to adapt, fix, I'm going to re-adapt again and fix, and so you can do that too. But if you weren't doing that, then yes, you would want to know this characteristic of the channel that you're communicating in. Okay, so we kind of talked about high level, the problems and the approach. Let's talk about implementation in actual software-defined radio, because that adds some additional complexities that we don't really think about when we look at this theoretical stuff, right? And I should actually scroll to this diagram, and it's pretty small. I don't know if you guys can see it, but this is the receiver architecture that we used for a burst receiver. And what it does is you have an input signal, and this part, so really the diagram would be better if I kind of showed the domains of processing here. At the receiver, you don't actually know when the transmitter is transmitting. And so some components of your receiver are going to be continually on. The burst part of it is going to only process the samples that it needs to process, but you need to know what samples to process. And so your receiver analog digital converter is continually running. So that's what this input represents, is the input from the ADC. Once you have this input, remember that we're doing burst signaling, and so we don't have meaningful information content in a large portion of the samples that we're receiving. So we don't want to process them, because that would just be a waste. So what we do, the first thing that we do is we do burst detection. And all burst detection does is, suppose I have, sorry, the mouse is kind of hard to see. Suppose I have an input signal that looks like this, and these are all my samples. Well, the burst detector, all it does is it picks out where there's energy in the signal. And you can do better. I mean, energy thresholding is a simple way to do burst detection. It's not the only way. This is kind of what we chose to do. But all it does is the whole point of the burst detector is to, in this stream of samples that I'm receiving, which samples should I process? And that's all it's doing. And it's looking for energy, and when it finds energy, It says, okay, I'm going to take this chunk of samples and then I'm going to shoot it down to the rest of the flow graph. I should actually put a picture of the flow graph because we do have it. We won't go through this code here because it's MATLAB. That might be heresy around here, but but we do have GNU Radio code as well that does all this stuff, and I'll point you guys to that at the end. But a lot of at least the way I do things is I kind of prototype things in MATLAB and then I'll port them to GNU Radio. So that's kind of where this stuff came from. But okay, so we have a burst detector, right? And the next step after burst detection is really intuitively. Let's go back to the picture of the adaptive filter, right? What the adaptive filter is doing is it's taking the received samples, comparing to the known samples, and then finding the optimal filter rates. So the only known samples of the signal that you know are the preamble, right? And so you have to actually detect when the preamble starts in this burst. If you look at this right here, you still have some dead samples before. You may have some spurious energy that just happened, and you detect that as burst, and you can't just adapt on that. So you have to actually detect where the preamble starts. In order to do that, you would just use a cross correlation. But you also have to be careful here, and this is why this part is kind of what I've called like the implementation part is you have to be careful when you do cross correlation. You can't just assume that your correlation peak will be high if you don't have coarse center frequency correction. The reason for this is that you really want to look at the properties of your preamble. And so preambles are typically chosen for really good properties, like they don't interfere with other preambles in like a CDMA system. Actually in GPS, you can kind of think of the CA code that the GPS transmits as a known preamble sequence, and a receiver will correlate against that to say, I have a satellite, right? But a receiver actually uses the frequency offset as part of its determination of your location bits in GPS. So the preamble in GPS, all that to say, the code in GPS is designed so that it's if it's frequency shifted by a small amount, actually your cross-correlation properties are not very good. In fact, you have to match your frequency offset in order to get the proper cross-correlation properties. So that's kind of the preamble that we had as well. And it's not going to, you can't just cross-correlate your burst against the preamble and expect to see a strong correlation peak until you have coarse center frequency alignment. And so the next step in an actual implementation is going to be to do center frequency alignment of the signal. We do that, we kind of cheat on that a little bit because we know that the signal is a PSK signal, and in a PSK signal you can actually remove the information content by taking it to the mth power. If you have an M PSK signal, you can take it to the mth power and you'll remove the information content, and what you have remaining is the baud lines and the center frequency offset. So that's exactly what we do. I'll show some MATLAB code. But it's really easy to understand. So if I have an input signal X, and I know that it's a QPSK signal, the M is 4 here. All I do is take it to the 4th power, and then all this stuff, all it does is it detects the center frequency offset. Once I detect the coarse center frequency offset, I can just correct for it by multiplying it by a complex exponential. So what we've done now is we've done burst detection, we've done coarse center frequency correction. Now we can determine the exact sample at which the preamble started. And all we do is a cross correlation, and that's what this line does right here. It just does a cross correlation between the burst that I want to equalize and the symbols that I know, the preamble symbols that I know. And then I can determine the maximum value of that and say this is the peak. And then you see what I did here is I actually just grabbed the samples from the start of the preamble to the end of the vector. So these are the samples that I want to correct. Another little SDR kind of not a quirk, but something you have to think about when actually implementing this stuff is now I've got the exact start sample. Well, typically in receivers, you'll set the sampling rate of the receiver so that you have n number of samples per symbol, right? Receivers typically do 2 or 4. I think 4 is a pretty common number, but you have something. And you have to have your adaptive filter rate matched to that same rate. And so the filter, because you're comparing sequences, the input sequence and the compared sequence need to be at the same sample rate. And that's all we're doing here is we have to make sure that we are rate matched. And so the filter that we did it at 1 sample per symbol. You can do more samples per symbol, and that's more processing, but it'll probably do a better job of it. So that's another thing where you can generate some curves and determine the optimal number of samples per symbol to operate at. But that's something that you have to make sure you do. So once you rate match your input signal, all you really do is you run it through this adaptive filter. One of the things that we need to think about is running it through the adaptive filter is pretty hand-wavy. And it works if you have a long preamble sequence. And that's because your input signal is pretty noisy, right? And so your adaptation rate, all of that matters in terms of your adaptive filter. So there's actually a closed form solution for the adaptive filter. It's called the Wiener equations. And that's what we did here is our preamble is really short compared to the burst, and so we couldn't afford to actually run it through the adaptive filter. So we found the optimal solution. Kind of running out of time, so I'm going to gloss over that. But we find the optimal filter weights. Then, and it's one MATLAB line of code. And then once you find the optimal filter weights, you just do the filtering. And once you do the filtering, you do we put a first order phase lock loop in there to correct for any constant phase offsets, although that shouldn't really be there. We did notice that it was there, and so we had this thing in there as well. And then you have your equalized signal. I don't have any diagrams to show the input signal, the input constellation and the output constellation, but actually Tim has some stuff where he uses his exact log and or exact code, and he has pictures of the input constellation and output constellation, so you can see those. Just to wrap up here, all this code is released in public, and it's on the GRBT GitHub under grburst. So it would be cool if someone took this and said, well, I want to do something general for any PSK signal, or really any PSK, QAM, and other kinds of modulated signals, so that we have some sort of general different way of doing equalization. And questions? Yes.
Does the generalized approach work for other modulations like FM?
So that's a good question. I don't think that. I mean, this depends on knowing. This method depends on knowing some portion of the signal that's being transmitted.
Right, but you can have if you have like a GMSK signal, you might have you have preambles and you've got a packetized data usually.
Right. Yeah, I mean, if you have anything that's known in the signal, then you can use this method. Some of the stuff in here is very specific to QPSK, like the center frequency correction. Right. But if you take that aspect out of it, you can use this approach. And it actually, in one shot, it corrects for time, frequency, and channel. So.
The other question I had was, when you're doing the cross correlation, you're just doing one operation, right?
What do you mean by
you're
one operation?
You're already course correcting for the frequency.
Correct.
Can you repeat the question?
Yeah, sorry. So your question was, the second question was, is when I do the cross correlation, I'm doing one operation.
Right.
Can you
So I was just getting. What I was getting to is there's probably noticed, like, because you were talking about GPS. With GPS, they're often when they're checking the correlation of the CA code. When it's implemented in hardware, they're like physically shifting
Correct.
a copy of the code back and forth.
Right.
Another way you can do that, which they usually don't do in hardware, it's harder, is
only do one operation. We do one cross correlation. Here, since we've corrected for frequency, I'm not doing a CAF processing. All I want to do is detect in time where my signal started.
I was wondering if this kind of assumes you've already taken care of gain. Like, let's say you receive a signal that's like really, really faint, and you're cross correlating against like a known good, as opposed to like correlating against like a previous
It does assume. So I'll repeat the question. The question is did I assume that the gain of the signal was taken care of? And yes, we did have a block that tried to do gain adjustment beforehand. I think that you're going to get, if you use an autocorrelation from the previous burst, right, you may take advantage of some of the channel effects that were there in the previous burst, right? And so that is another approach we could try and see how that compares.
I'm sorry, PSK is constant envelope. You really should just be able to look at what you think is a preamble and do
Right.
just an AGC based on that.
Right. Yeah. So that's a good point too.
All right. Well, let's thank our speaker. Thanks very much, Kieran.
Sure. Thanks. Thank you.
So we'll head now to our final speaker. So we're going to hear from Tim Keaston now as our final speaker. Is VG a good thing?
I hope it is, because that's all I got.
All right, and generally we'll try to have this short period of time where speakers are setting up to have any announcements. So I don't really have anything significant now myself, but if anybody might have an announcement of something they'd like to make quickly, just feel free to stand up and shout it out. Anyone? No? Pardon? Magic tricks? I haven't got any magic tricks, but John Malsbury, my friend and former colleague who works at SpaceX, and we work together on the IC3 reboot mission, has just called me. Hi, John. Hello? We're having the meetup now.
Put him on speaker.
I can't hear him. Are you there? It's a bad connection. I'll call you back later. Sorry. So I'll hand it over now to Tim. Looks like you're all set up. Take it away, Tim.
All right. Well, hello, everyone. It's awesome to be here. I was telling Dalen a couple of days ago that I've always wanted to come to Cyberspectrum, like really badly, but he always has this really bad habit of holding them in California. So I'm really excited to be here and a little bit nervous because I have a lot of respect for some of the people in this room. GNU Radio community has been really awesome at teaching me all this stuff, making it not head knowledge, but something practical. So here it is. I'm here to teach you something about that I learned. So I went, a lot of the work that I've seen people do with GNU Radio, they'll start reverse engineering something like a doorbell or a key fob. And they get their packets into Audacity, which is a program for editing sound waves. And they sort of draw lines on it with MS Paint, and they're like, ta-da, finished. That is where I started too, and that is a great way of doing things. But it's not all you can do. There's so much more that you can do it. So what I wanted to talk about was sort of how you could transition away from just sort of looking at the signal and actually doing things with it. So I'm gonna just do a quick talk on how to do the outline of my talk. Like I said, I'm a little nervous. Outline of my talk, I'm gonna do a quick replay attack on this shock collar that I have. And then I'm going to move towards doing some real-time packets, understanding how the packet is formatted, and then doing some transmissions too. So the background story for this is that I went to DEF CON, and I've been recently told it wasn't DEF CON 23, it was DEF CON 25. But in the Wireless Village, which was organized by some really great people, they had this fun game where you could try and capture a transmission from a shock collar and replay it to shock yourself for points. Hackers will do anything for points. So I actually reverse engineered it while I was there, and just had a lot of fun with it. So this is sort of the write-up for that. So I went on Amazon and got it. It was a great deal. I saved $100, almost $120, and you can use it with all types of dogs, like German Shepherds and Yorkshire Terriers, and their customer service is really helpful. I like that they don't indicate that this is the wrong type of product to use for a cat. They're just like, no, it's the wrong size. So. Okay, so replay attacks. The replay attack is a pretty simple to understand. All you have to do is overhear the communications between this, and when you play it back, hopefully something happens. The idea is that the software-defined radio is acting sort of like a tape recorder. When the transmission happens, it just records it and plays it straight back. So when the transmitter's out of the picture, you should be able to take whatever they sent and have it happen again. Now, obviously, this is sort of a bad thing, especially for things like cars. It would kind of be bad to go and unlock your car in the parking lot and come back and find out that it's gone. So some newer technology is implementing rolling codes or some sort of handshake between the two to do that. But for a $30 device from Shenzhen, it's not going to have any of those sort of protections. Also, by the way, I have code written that I literally wrote in 20 minutes on the way down here. I've prepared all of 8 hours, so if you were to be warned, something might break.
What could go wrong?
Yeah, right. With the shock collar, nothing. Okay, so to record, a lot of people use a program called GQRX, but my program of choice is Osmocom FFT, which I'm going to increase the font size so you can see what I'm typing. Look at that. The reason I like this is because it lets you use something like Phosphor, which if you have been around for the past few days, you know that this is a really, really awesome piece of equipment. So I'm going to tune into, let's see, where I want to tune in. Yep. I'm going to tune into the 433 megahertz band, because that's where this guy transmits. And I'm going to up my sample rate just a little bit. And I've got a lot of gain, and I'm really close to this device, so it's kind of going to be shouting. So I'm going to turn down the gain a little bit so that you can actually see the signal. So let's do a quick transmit. So yeah, I'll save the shocks for later. Let's just have it beat. So you'll notice when I push down the button, you see transmission happening up in the corner. And one of the interesting things that you want to do when you're capturing a transmission like this is you want to make sure that you don't have too much gain. If you have too much gain, it's like distortion. Just like when you're listening to an audio that's got too much volume on it, it starts sounding scratchy. So if I turn the gain up too much, you can see my signal starts to distort, and I have harmonics showing up on the sides, which is really, it can make it very difficult to receive your packet. So I'm going to turn my gain back down. You also want to make sure that you have an appropriate sample rate, and a sample rate here. Hold on. Oh no, I shouldn't have tried that. Oh crumbs, I'm going to have to restart. So I thought it would be really cool if I could show zoom in on my laptop so you could see what I was pointing at. Unfortunately, using OpenGL twice does not, yeah, it just doesn't like that at all. Anyway, so the sample rate is really important. That is how much of the spectrum that you're seeing at one time. You obviously need to have enough that you can see your signal and frame it correctly. But you don't want so much that all of a sudden you've got like a 2 terabyte file on your hard drive, because that's kind of hard to analyze. 1 megasample is sort of my go-to for these low baud rate sub-gigahertz ISM things, because most of them fit in it, and also devices like the RTL SDR can support sample rates like that. Obnoxiously long password. So there's this great time my professor started typing her password in the username field, and she was like, don't look. It shows on your hands. You can't really do anything about that. Okay, let's get that up again. All right, sorry about the little glitch there. I won't zoom in anymore, so if you're on the internet, sorry. All right, 433 megahertz, 1 megasample. And let's get rid of our gain. Also, you'll notice there's that really big spike right in the center of my waterfall. That's an unfortunate side effect of the way the Blade RF was designed, and we're going to deal with that later. So I'm going to give my file a name. I'm going to call it beep, because that's what I'm doing, is I'm making it beep. This thing has 4 modes, by the way: beep, shock, vibrate, and flash. So that's recorded. Do a transmission or two, and we'll stop. Okay. Yeah, it's got a. This is a motion sensor in it to stop. So if the dog stops moving, it turns off. So that's a great way if you're a dog and you're listening. This is a great way to be misbehaving and get away with it. All right, so I'm going to open up GNU Radio Companion, and I'm going to replay this. There aren't really any tools for taking a file and just putting it back on the RF spectrum, so you have to build it again. But it's pretty simple. It's not too hard. What you do, all right, let's see if Zoom works this time. Whoa, no, it didn't. Oh, okay, so it's 2 displays. All right, so while this is up, man, I might be able to salvage this. Yes. Okay, so 2 displays and zooming just does not work. Oh, man.
There's your password.
Don't worry, I have Google Authenticator on my Gmail account. Oh, good night. Sweet. Oh, gosh. All right. You know what? This is just going to be faster to turn it off. This is gonna Sorry, guys. Boy, that's really unfortunate. Okay, anyway, so our general idea here is that we're going to take our RF, and there's going to be this block called the file source. That is going to read the RF capture from the disk and spit it out that little blue tab that you've probably seen on the screen before on my computer. Spectacularly crashed. Those samples are going to go out, and ideally, we'll just send them straight out, careful, to the antenna again and have it transmit. But we're going to do a little bit of post-processing on them just to clean it up, because that DC spike can actually make life really miserable for us. Hey, I typed it in the right. Didn't have to get sudo. All right, note to self: shorter passwords are better. How much? Balin, what was our hard limit on time? Quarter past. Okay, so I'm still moving. Alrighty. I'll show you real quick what the DC blocker does. The DC blocker is a great little block that removes that DC component. I know I'm tuned into 433.75 megahertz, but as far as the radio is concerned, it doesn't know where I'm tuned, so it just calls the center 0 hertz, right, or DC. The DC blocker looks at the signal over a period of time and says, hey, it looks like the value is not 0 as it should be, it's a little higher, and so it subtracts that out. So when I run this, oh, okay, I'm going to have to recapture, because when you reboot, you lose your files in temp. Boy, demo gods are not shining on me today. Alrighty, we got to do this quick. We're running out of time. Beep. All right. 433.75 megahertz. All right, and wow, these values are totally off screen. Okay, 1 mega sample. Record. 3rd time's a charm, guys. 3rd time's a charm. All right, we're good. So coming back, I'm gonna open my file in temp. There we go. And so again, the last thing is the throttle block. My hard drive is really good at reading files very quickly, and so the samples would be coming out infinitely fast, which would bog down my computer and likely crash it again. So the throttle block is a useful tool for slowing that down and only reading it in blocks that give you about 1 million samples a second. So I'm going to feed this into the phosphor sink. Cross your fingers. All right, there you go. So you see that notch that's in the at the DC component right there? So that's cut the DC component right out, and now I don't have my signal competing with something else. Actually, I do. It's just I'm going to have another DC spike on the transmit, but at least I don't have 2 DC spikes on the transmit. Okay. So I can now disable this half of the spectrum, or this half of the block, and enable this one. Osmocom Sync, for those of you that don't know, there's about 4 or 5 different hardware radios that exist. And the Osmocom block is one that acts as an interface for all of them. Sort of.
So the parameters that I set for it are just the same as my capture. I captured it 433.75, and I have some gains here. So with any luck, the demo gods will shine upon me. Okay, there we go. Right. So what we've confirmed is that as far as we can tell so far, this is not using any sort of rolling code or anything like that to add security to this device. So let's see if we can actually get a better and closer look at what's coming through this. So we know it's on-off keying because it has that single spike. Is anyone here not like an RF nerd? Okay, good. Awesome, I'm with brothers and sisters. Okay, so whenever you see that big single spike, it's on-off keying, just like Morse code. And the tool that we're going to use to get samples out of that is going to be the complex to mag block. And I'm sorry, I can't zoom in, so if this is about as good as it's going to get. The complex to mag block takes the complex magnitude of your RF signal coming in and turns it into a waveform that you can see. This is what people are sending into Audacity. So I'm going to grab my throttle again because failure is not an option. No. I'm going to grab the Qt GUI time sync, which is like an oscilloscope for looking at waveforms. And we're going to put these in, and we should see something happening on the screen. And look at that, we're starting to see bits come out of our screen. Or at least for a brief second, you saw a couple glimpses of that. What's happening is the oscilloscope is looking at every portion of the file as fast as it can. The problem is most of our file is boring and has no content in it. So I can set up a trigger and say, wait until the waveform crosses this threshold here. And when that happens, I want you to display what you have in the next buffer. So I'm going to pop out of this real quick. And there is an awesome control panel. Dr. Tom, are you here? Nah. All right, well, he coded that, so thank him. So I'm going to set my trigger up to normal. And when I increase my level, you can actually see the waveform coming and going. But we have this huge block of samples, right? This is part of the preamble, and we can't see the rest of the packet because there's just way too many samples for us to see. To give you an example really quick, if I have 1,000 samples for this one block, that's way too much for your process. You know, I'm sorry, I'm going to come back to this in a second. I'm just going to throw away some samples so I don't have to see so much. So I'm going to grab the rational resampler, which is a great little block which lets me interpolate and decimate my signal as needed, and connect it into my system. And, oh, Dr. Tom Rondeau is missing this. I'm using his block. He is a huge evangelist for the polyphase things. All right, and I'm going to go pull a magical constant somewhere. Don't look. It's going to be coming. All right, what am I using? 18.934. There we go. So I'm throwing out a huge amount of samples. What this is doing is it's literally, you know what? It's magic. This block is magic. Alrighty, so now that I've got my trigger set up, you can actually start to see bits and pieces of the packet. Unfortunately, I don't have the window scaled properly, so the packet's going to be wiggling around a little bit. It's really nice if you have everything set up nicely with your window, because then you get this stable packet that you can look at. But what you can see here is a very unusual sort of form for anyone that's used to seeing digital codes. If you're used to doing signal processing like the previous presenter was, you're used to seeing your bits come in nice square-shaped blocks, and every bit is the same as the last. And I'm walking off screen. A lot of these really inexpensive devices don't use that at all because they don't want to have to do clock recovery because it's very difficult to do clock recovery. I tried to implement it. It's hard. What they're doing instead is they're looking at the positive edge here. Whoops. You know, maybe I should stop pushing buttons here. Did someone... I'm in dangerous territory tonight. All right, so they have this going straight into a little microcontroller of some sort. And what they're looking at is they're looking for this positive edge. And when they see it, they wait a brief period of time, and then they sample the data to see what it is. So starting here, they see the positive edge. They wait a period of time, and oh, that's a 1. And then after that, they have a guard period, because if it just stayed high, they'd have no more positive edges.
So here's their positive edge again. They wait a period of time, and then they read their sample, and that's a 0. Now, I could sit and put this inside MS Paint and start drawing lines in 1, 1, 1, 0, 0, 0. But for very long packets or packets that change very quickly, or if you have a system that actually, I did a temperature sensor once, right? Look, just get a packet. Don't go blind trying to work with doing screenshots in MS Paint. Although, I have done that before, and it does work. I do have some more slides really quick. I think that I need to demonstrate, go through. Oh yeah, so here's the idea, right? This is your RF spectrum, right? There's a lot around the whole world, but we can only look at a brief window when we quantize it. And we have a big nasty DC spike in the center. So if we tune off to the side, we can get a picture, at least somewhat of a picture. We can deal with the DC spike later. So there's some more things that I wrote. There's our 2 megahertz or 1 megasample of bandwidth. So when I did 1 megasample of bandwidth, I could see from 434 to 433.5 to 435. So, right? Yeah, so there's the standard data for those of you that have actual clocks and signals, but this is not like that. We have our frame bits where we have a start and a stop bit, and the data in the middle. Right, coming back to that in a second. Right, so how are we going to decode this? Unfortunately, just because of the way this packet's structured, and I'm going to be running out of time real fast, so I can't show you all this stuff. You can't use any of the blocks that are in GNU Radio to get this packet out. So I wrote my own. And it's not too hard. I can show you the general process here. So we use this really cool tool called GR Mod Tool. It comes with GNU Radio when you install it. And I do new mod. I'm going to name this Really Bad Ideas. Okay. And now I can, oh, there it is. Now I can create a new Python block. Someone's like enjoying watching this happen again. We can create a new Python block to handle this. So GR Mod Tool, add block. No, new block. Add. Yes, okay, and it's going to ask me what type of block do I want. By the way, who's never coded a Python block? Learn? Only one person. Okay, if you work with GNU Radio, learn Python. This is really cool. All right, so we want to sync because we want the samples that are coming into the system to be processed by our block. And of course, we want to do Python and not C++, and we're going to call this shock color sync. We're not taking any arguments. And who does QA code for something like a shock collar? Okay, so here is the code. Everyone read that okay? If you can't, sorry, deal with it. All right, this is the work method where we process our samples. Okay, so I can do, come on now. I'm not actually writing this whole thing here, by the way. I actually have code that I'm running. This is just to give you the idea of how simple it is. So for sample in 0, where in0 is the buffer that we're going to be processing. All right, what are we doing? We're looking for a positive edge, right? We're looking for that positive edge, so we're going to say if sample equals 0 and last sample equals 1. Well, where's our last sample? We'll get to that in a second. We're going to do something here. Else, can't write Python. Sample equals 1. This will be our negative edge. More stuff here. Okay. Now to save state, I forgot. We can add this to our object so that it's saved between function calls. So we're going, as this is happening in real time, we're going to be getting blocks and blocks, and blocks of code. So we're going to have to be able to remember where we were for that last sample. So this lets us store this within the block. And then from there, we can do something like set up as a little tiny state machine. When I see the positive edge and I was previously in the idle state, count the number of samples until we see the next falling edge, which I basically did here. And in fact, I even added some debugging so that I could see what was happening. So I'm waiting for, in the idle state, when I see the first positive edge, we've hit the preamble. It's not really a preamble, it's just a block where it's all ones. I wait for bits, and then I add it to a buffer that I've got somewhere in my program. And then finally, when that buffer is complete, I pass it on to be processed later down the road. So let's take a look at what that looks like. So here's my flow graph. I'm not going to be using the RTL anymore. Okay. So I've got my my Osmocom source tuned to 433. I have a low-pass filter to sort of get rid of signals that might be in the area that I don't want to deal with. I demodulate it. I throw away samples so that I'm not processing a block of 1,000 samples per bit. I'm only processing a block of 20. Boy, I wish I had time to talk about this. I don't. Sorry. Then I slice it up into binary and I pass it into my sync here. And my sync is what handles the messages and decides what's going on. So why are you yelling at me? What's wrong? Oh, bread muffins. Okay, we're gonna have to run this one. I updated my code. This is what happens when you update your code before a presentation and you don't have time to fix it. Okay, so we'll do a quick transmission here, and what you'll see is you will see the messages pop up down here. Ah, yes, it worked. Okay, woo! All right. So there's our message right there, and I actually have it decoded here, but I'm going to show you the process of decoding. So when you're reverse engineering a signal and understanding it from outside of, I guess, knowing how it works beforehand, you have to make some guesses, and sometimes you make guesses that are wrong. Like, oh my gosh, the volcano is erudite. Okay, so what field should we expect in this packet? Obviously, we're going to need a command, whether we want to shock our dog or just vibrate and give them sort of a warning that they're doing something bad. We're going to need a caller ID, right? So if we have 10 people in the park that all bought this magical, wonderful device, we don't want everyone's dog getting shocked at the same time. There's also a shock level on this that you can choose how bad you want to spank Sparky. Interestingly enough, the shock level goes between 0 and 100. And if you have it on 1 because you're really nervous about hurting your dog and you bump the button backwards, it goes right to 100. Know how to use your device. And hopefully some sort of checksum. If there's an error in the packet as it's being transmitted, we don't want to, we don't want the caller saying, sorry, did you say 100? No, 10, 100? Okay. So we want some sort of checksum. So these are the packets that came out. And it's kind of nerve-wracking looking at this big blob of binary data. So we can do some things to help understand it. The first is all of these were captured with a value set to 20, which is really helpful because 20, well, we might be able to find that inside our stream. Sometimes the packet data, sometimes people like to encode information differently. Since this only goes between 0 and 100, they might have scaled it to go between 0 and 255. Or they might have encoded it in ASCII, who knows, right? Fortunately, I did a little bit of looking, not there, but oh hey, winner, winner, chicken dinner. There's my hexadecimal or binary 20 inside the packet. So I lucked out. And I'm assuming this thing is using 8-bit boundaries because it's probably got some sort of microcontroller in there. So if you divide it up into 8-bit boundaries, you notice that these next 16 bits on the left are always the same in every single packet. So that's probably our caller ID, right? And if you sort them, notice what I did there. Does anyone notice a little bit of a pattern? Everybody see a pattern? Yeah, right. So we're seeing we have 4 different types of commands being sent, or at least 4 different messages being sent. And I'm not telling you what the order is, but yeah, these are the different commands. So that just leaves us, yeah, if anyone can't see it. Yep. So it just leaves us with one last field. And also there's like 2 bits at the beginning and end, which really throw you off if you try to look at those. What is going on? The last is our checksum. And the checksum you expect, maybe they're doing like CRC or they're doing like some part of MD5, and it's like, no, they're actually taking the command and turning it backwards and inverting all the bits. So you can see your 0 marching across the screen right there, which is really, really bad because that means that if there's some sort of noise that corrupts, I don't know, maybe the level, they have no way of detecting it at all. But what do you expect for a $150 device that they're selling for cheap? This raises some interesting questions. Now that we have an understanding of how the packet's formatted, we can start transmitting our own. What happens if we turn all of them on? Can we
beep, blink, vibrate, and shock all at the same time? Because I mean, there's like some people in Japan that would be all over that. What happens if we set the level to 255? Because it only goes to 100 here. I'm not brave enough to test that. So I have one last demonstration to run. So I actually built the full-fledged transmitter. I built the other side of this so that you can transmit messages and receive them. So if you scroll down just a little bit, you can see actually the easiest way to get asynchronous messages into GNU Radio is the socket PDU. So my shot collar is controlled on the internet now. This just keeps getting better. So what this does is this looks for a command from netcat or some telnet program, passes it onto this, which wraps it up into a form, the packet, generates the samples, which then go out eventually and are transmitted with the Blade RF. Let me just make sure I didn't change anything else on this. Okay, so we should have something working here. So let me start this up. Alrighty. Alright, so if I run wake up. Okay, so we can transmit a message and have it beep. What happens if we do beep? Bep. What happens if we do beep 100, right? So you can't really change the beep level for this. So what happens when you do beep 100? Nothing exciting. Sorry. Got you guys all excited for nothing, right? What happens if we do, but you can do vibrate 10. And I don't know if you guys will be able to hear this, but it's really low. And if you do vibrate 100, right? So we've got pretty much full control over this. And I also had it so that you can specify which color you want, which lets you do really, really nasty and evil things. Where did I put this? I forgot where I put this file. So, so it stands to reason now that I can receive packets and I can also transmit them, I can do information with that. So I could sit in a dog park if I was really so evil, and I could listen for people to do transmissions, and when I see that they're trying to get their dog's attention with the beep, I should be like, no, you should get your dog's attention with a shock. So, I mean, what kind of engineer or mad scientist doesn't test out his own stuff, right?
This is the high-tech version of poisoning pigeons in the park.
Yeah, something like that.
Replay.
Yeah, something like that. All right. So here we go.
Not
I'm going to set up. I have literally tested this one time just before I came in here. I really hope this works. Oh, wow, maybe I should turn this down from 100. Whoa! Okay. Near catastrophe averted. Okay, so what this program is doing is it's connected to the server side of things, and it's looking at what gets spit back. Because when the server detects a packet, it actually sends it back to say, hey, I saw this. Did you want to do anything with this? And it's like, yes, I did. If I see beep and the same caller ID 3 times in a row, because remember, the caller ID isn't part of the checksum, right? So I have to sort of keep track of this myself. Once I see it 3 times in a row, I wait 5 seconds and I say, take that caller ID and give it a shock. So
can we get a good shot of it?
oh, you're just getting
You can put it on.
Pull the
There's-
the pen up a little bit.
And what am I, like showing off like more wedding like
Yeah.
that? There you go. All right. Anyway, so I have really no idea if this is gonna work. So we'll see if it pops up on the terminal. If you see me jumping and screaming, you'll know. I should have given this to Balin and be like, if I make any puns about shocking. All right, here we go. Oh, it's party time. Okay. 5 seconds. Okay, so to wrap up, does anybody know what this is? This is actually my coworker's joke. It's a fur filter. Okay, so record. I didn't get time to do the regeneration, but record, regenerate, and replay and see what happens because you never know. But once you've got that done, there is more things that you can accomplish.
use the Qt GUI syncs and look at your signal and actually try and get bits out. If you use the clock recovery block or some of the packet formatting things, you can pull out the bits from it and you can do a lot of really cool things with GNU Radio. And hopefully someone's watching this is like, hey, I'm developing a wireless device and maybe I should actually put some thoughts towards security. Yes, you should. Build full-fledged receivers. I didn't have time to demo this either. I was going to show you how you could filter noise out, and that's like the DC blocker part. The further this signal gets away, the weaker it gets, but you can do some pretty amazing things and still recover it. And finally, packets are amazing. You should do stuff. So, do I have time for questions?
Yes.
All right.
Questions.
Any questions, anybody?
Did you want to quickly talk about the DC removal and filtering?
Do we have time for that?
Sure, a couple of minutes.
Okay.
I mean, you just shock yourself for our benefit and amusement, so the least we can do is give you a couple more minutes.
All my demos work. I'm pretty excited about that. All right, this is just really fast. I don't have time to show it through the whole thing, but hopefully inside here you'll get just enough of the idea that you'll be able to run it with it on your own. So what I've got right here, and I can't zoom in, I'm really sorry. I've got a square wave that I'm generating up here to simulate some sort of regular data, and I've got some noise that I'm adding to it down the line. And of course a throttle block, and I'm throwing it into a Qt GUI time sync. So as you can see, if this was the data that we were receiving from our on the receive side of our tool, this is pretty unintelligible. It's kind of hard to do any work with that. But if you throw a filter on there, you can try and smooth the lines out on that data. For any of you guys who have worked with Excel before and done a moving window average where you just average a whole bunch of columns, it works pretty similar to that. So I'm going to grab the single pole IIR filter, or infinite impulse response. Just going to hook this puppy up. And I'm going to configure the alpha parameter inside this block to be controlled by this range. So I can actually change and figure out, hey, what should I use for my alpha parameter? All right, so again, my noisy signal. And as I start bringing my alpha parameter down on the IIR tab, you can see that my signal is starting to clean up slowly, slowly, and surely. So this is now a much cleaner signal that we can use to process. But we're going to have another problem in a second. So this one's centered around 0. But what if our signal is not centered around 0? So give me just one more second. Get rid of my offset. Whoa. Alrighty. Okay, so in my program, I need to make a decision. What is a 1 and what is a 0? And the way you usually do this is you set some arbitrary threshold and say, once it crosses 0.25, we're going to consider that a 1. But you don't have the luxury of knowing that your signal will always be at 0.25 or more than that or less than that. In fact, sometimes there could be, if like there's a interferer, like that DC spike, this whole waveform would shift up and away from that, and you might just get all zeros. So we need some way of taking our signal and automatically determining, given the base of our signal and the height of our signal, can we sort of remove that DC aspect to it. So we're going to use the DC blocker again, but we're not going to use it exactly in the way that we used it the last time. The last time we were using it to remove the DC component from RF. Now we're using it to remove the DC component from our data. And there's, I wish I had the ability to explain that tonight. My mind is just like, done. Yeah, this is a shock, right? So I'm going to grab my DC blocker again. Let's see, what do I got? 32K, 100. I need to figure out how long I need to set my DC blocker. I actually can't. So I need to tell it how many samples to look over to compute this average. I'm just going to throw a stupid crazy value in there and run with that. And it doesn't really show very well here. But you can see that my signal used to have a DC component and now it's shifted down. Hey, actually, you know what? I can show this in the, I can show you in this block over here. It looks pretty wacky. You might have heard about data whitening for your signal, where you want your signal to have equal number of 1s and 0s. This is why. It's so that you can automatically decide where. There we go. You can automatically decide where 0 is. So I have a DC blocker on this signal here. And you can see that it's actually wiggling around a little bit. There's a bit of a wave to it. That's what's happening when you have long periods of zeros. Those long periods of 0, it's saying, it looks like the DC component is over here. And it's trying to calculate that, and it just
it can only do so much magic. A better way of solving this problem is using Tim O'Shea's PyQt blocks, where you grab the whole message and I can look at it all at once. Right now, I'm sort of looking at it as it comes in, so I'm trying to do a best effort. But let me see if I can remove.
That's all you need.
Yeah, right. If I remove my antenna, I might be able to show you what happens when you have a weaker signal. And after that, I'll take questions and sort of wrap up. There you go. So see how I've got a weaker signal down there? I'm going to need to zoom in because it's really weak. Okay. But the cool thing is, even though this signal is so small and really weak, and I'd be losing it otherwise, I'm still getting packets that work. So that was sort of the idea for full-fledged receivers, and now I'm kind of done. Any questions? No animals were hurt?
Except for you.
No.
All right. Well, thank you for putting your body on the line to demonstrate.
You guys
that.
are more than welcome.
Interesting attack. All right. So thank you very much once again for coming out. Let's thank our 4 speakers one more time. And I actually recorded you shocking yourself. I'm just about to put it on YouTube and tweet it out so we can relive the joy and the pain over and over. So thanks again for coming out. Thank you to VT and Hume Center for having us able to be here. And we need to exit the building pretty promptly because, as you probably noticed, the air conditioning has been turned off as well. So thanks again. See most of you tomorrow. And if I could please ask you really kindly just to grab all your belongings and cups and whatever else is lying around and just dispose of it